Now that we have our platform implemented, we can export the hardware for application development in Vitis or Xilinx SDK. If by default the pre-synthesis is selected, you have to make sure that you include the bit stream. Now let's create an application in Vitis for this platform. Make sure to select the exported hardware that we generated from Vivado. I will start with the template for Hello World. Let's build the platform libraries and the Hello World application. Okay, the compilation finished. To make sure everything is set up properly, I will run the Hello World application on my GCU104 board. Okay, now the debugger has hit the first breakpoint, and I will start a serial terminal. So I will be using Picocom as my serial terminal, but you can use whatever you are comfortable using. So what this command says is to start the Picocom at baud rate 115200, which is the baud rate for my UART, and my device is connected connected at /dev/tty USB1, and I'll be logging my session in this file. Okay, so the Hello World was printed, and that means my platform is set up correctly. To use IMAGine, I have provided its driver as C source files. Now I will add them to the Vitis project. The driver can be found under the supplement directory under the proj GC1040 and the IMAGine driver. The driver provides very low-level access to the IMAGine IP. The push instruction function pushes one IMAGine instruction into its input FIFO. If the vector output instruction is issued on IMAGine, it generates the end of vector interrupt when the entire output vector has been pushed into the output FIFO. The isEOV function returns true if the end of vector interrupt is set. This function can be used to poll this flag if interrupt service routine is not set up. The clearEOV function clears the interrupt flag. The test function performs a basic test on IMAGine based on a hard-coded 64-bit number. The pop data function returns one element of the output vector, popping it out from the output FIFO. These just-in-time assembly functions are provided as mnemonics corresponding to the assembly instructions of IMAGine. The most important one is the load vec row, which can take an array of fixed point values and load it as a row vector in a register of IMAGine. The first thing we want to do with IMAGine is to verify if it is set up properly running the IMG test function on our application. So let's do that. Okay, so now we are in our debugger and we can step through the IMG test function. So the IMG test function reads a 64-bit magic number which when printed as an ASCII string prints the string IMAGine. So now that it prints the correct magic number, we know that the IP has been set up with the correct address map. To ease the application development using IMAGine, I have also provided a basic utility library as C source file. The IMG push program function pushes an entire IMAGine program into the input FIFO. The pop vector pops out the entire output vector from the output FIFO. The pop vector F works the same as pop vector with an extra step to convert the output fixed point to floating point values. These utilities can be used to convert between floating point and IMAGine's internal fixed point representation. The print float function prints the given floating point number as a ASCII string. PollEOV blocks until end of vector flag is set. PollEOV MSG works as PollEOV but prints a message while waiting. In another video, I will show how to write an assembly program for IMAGine from scratch using the IMAGine Assembler Python module. For this demonstration, I will use a precompiled program that implements a single layered MLP using IMAGine for the GEMV operation. Apart from the driver and the utilities, this example has three source files and one header file related to the program we will be running on IMAGine. The header file defines a struct that holds an assembled IMAGine program. The loader program will be used to initialize the PE registers of IMAGine with the weight matrix and the bias vector. The kernel program performs the GEMV operation using the values stored in the PE registers of IMAGine. To test the correctness of the program, I have also generated some test vectors. One input vector and the corresponding output vector. In the main program, we declare these constants related to the IMAGine kernel. The kernel expects the input vector to be stored in register 2, which is represented by the constant regv. Let's run the program. The main program at first performs the basic tests to make sure the address map is correct. The load parameters function simply pushes the loader kernel of the IMAGine program. Then it tests the kernel using the test input vector. It loads the test input vector using the load vecro just-in-time assembly instruction. Then it executes the kernel program, which computes the GEMV using the test input vector. Finally, it pops out the output result of the output vector, which is the result of the GEMV operation. Then, in this loop, it compares the output vector of the GEMV operation with the expected values. As we can see, all of the values matched. The length of the output vector of this kernel is a 16 element column vector. Now we know that our kernel program is running correctly. Now we move to the free running part of the application. In the application, we are assuming the input vector is generated by a sensor on the fly. So we read the input vector from the sensor and then run inference on that input vector to get a classification result. Inside the inference function, we at first load the sensor data into the input register regv. Then we run the kernel program on it. Then we read out the output vector. Then we use the argmax function to get the classification result. After getting the result, we can do something with the classification. Here I am just printing out the result. The main program keeps doing the same thing again and again. So basically it reads the sensor, runs inference, and use the inference result to do something useful. In another video, I will show how to generate the IMAGine kernels like the one we used in this example program, like a EX01 kernel or the EX01 loader program, using the assembler module packaged in the evaluation zip file.